The last star in a dying universe will flicker out roughly 100 trillion years from now. After that, the cosmos will enter an age of such profound darkness and cold that the very concept of event loses meaning. No light, no heat, no movement worth measuring, just the slow, grinding arithmetic of entropy doing what entropy has always done, spreading everything thin until there is nothing left to spread. We know this. Science has worked it out in careful, unhurried detail. And the fact that we know it, the fact that human minds, assembled from stardust on a small wet rock, have calculated the obituary of the entire universe, says something extraordinary about both the cosmos and about consciousness. But here is what haunts the edges of that knowledge. We have mapped what happens after the death of stars, after the death of galaxies, after the death of black holes, and in doing so, we have stumbled onto something that looks less like an ending and more like a question that keeps refusing to stay answered. This is not a story about heaven or hell. It is not a story about the soul in any religious sense. It is a story about what physics, cosmology, thermodynamics, and quantum mechanics actually say happens when something, a universe, a star, or a mind, ceases to function. And what they say is stranger, deeper, and in some ways more unsettling than any theology ever managed. If you enjoy deep space explorations like this, consider subscribing. To understand what happens after death, we have to start where science starts, not with sentiment, not with hope, but with definitions. Death, at its most fundamental level, is a transition in the organization of matter and energy. It is not the disappearance of anything. Not one atom is destroyed when a star collapses or when a body stops breathing. The atoms persist, the energy persists. What changes is the arrangement, the specific, improbable, information-rich configuration that made the thing what it was. This is the first and perhaps most important thing thermodynamics teaches us. The universe does not destroy. It transforms, and it transforms in one relentless direction. The second law of thermodynamics is one of those rare scientific principles that seems to carry genuine philosophical weight. It states that in any closed system, entropy, the measure of disorder, of the diffusion of usable energy, will always increase or stay the same. It will never decrease on its own. This is not a tendency or a preference. It is a law in the most absolute sense physics allows. You can fight entropy locally. Living organisms do it every second, burning fuel to maintain their impossible internal order. But the price is paid elsewhere. The local decrease in entropy is always more than offset by the entropy increase in the surrounding environment. Life, in a deep sense, is a very elegant way of accelerating the universe's overall journey toward disorder. What this means for death, for any death, stellar or biological, is that the organized structure that defined the living thing does not simply vanish. It disperses. The information encoded in that structure spreads outward into the environment in forms that become progressively harder to recover. The heat released by a cooling body drifts into the air. The atoms that composed it are borrowed by bacteria, then by soil, then by rain, then by a tree, then by the insect that eats the tree's leaf. Nothing is lost. Everything is redistributed. But is it gone? That is the harder question. And to answer it, we need to think carefully about what information actually is. In physics, information is not an abstract concept. It is a measurable property of physical systems, the precise specification of the state of every particle in a system, the position, velocity, spin, and all other quantum numbers of every constituent. This information is, according to the current understanding of quantum mechanics, conserved. It cannot be destroyed. This principle is sometimes called the conservation of quantum information, and its implications are among the most debated and unsettling in all of modern physics. When a book burns, the ashes and smoke and heat contain, in principle, all the information that was in the book. The text is not gone. It is encoded in the precise trajectories of every carbon atom, every photon of light released, every vibration of every molecule. It is irrecoverably scrambled from any practical standpoint. You could not read it, but it is there. The universe has not forgotten. This is not a comforting idea so much as a structurally significant one. It means that the universe keeps records, bad ones, written in a language of quantum states that no macroscopic reader could ever decode, but records nonetheless. Every configuration that has ever existed leaves its imprint on the configuration that follows it. The present state of the universe is, in theory, a complete ledger of everything that has ever happened in it. The history of every star, every creature, every thought is engraved in the fabric of what exists now, just impossibly compressed and scrambled. This is the context in which the death of a star has to be understood. When a massive star exhausts its nuclear fuel, when the outward pressure of fusion can no longer balance the inward crush of gravity, the core collapses in a fraction of a second. What was a star the size of several suns compresses down to a sphere roughly 20 kilometers across. The temperatures reached in that collapse are beyond any ordinary intuition, hundreds of billions of degrees. The outer layers of the star are blown into space in a supernova explosion that briefly outshines an entire galaxy. The light from that explosion travels outward at the speed of light, which means it is information traveling outward. Specific information, the spectral signature of the elements in the star, the precise intensity curve of the explosion, the timing of the shock wave's propagation. Astronomers thousands of light years away can and do read this information. They reconstruct the life history of the star from the dying light it sends outward. This is not metaphor. This is literally what stellar spectroscopy does. What remains behind after a supernova depends on the mass of the original star. For stars of moderate mass, the core collapses into a neutron star, a city-sized object so dense that a teaspoon of its material would weigh roughly 10 million tons on Earth. The protons and electrons of the original stellar material have been forced together into neutrons, packed at nuclear density across an object about 20 kilometers in diameter. The surface gravity is 200 billion times stronger than Earth's. The magnetic field is trillions of times stronger than any magnet we have ever built. A neutron star is death transformed into something almost incomprehensible. The star is gone. The fusion reactions have stopped. The light has ceased, but the mass is still there, organized now in this extraordinary, ultra-dense configuration. It rotates, often hundreds of times per second, beaming radiation from its magnetic poles like a cosmic lighthouse. These are pulsars, and they are so regular in their rotation that they were briefly, seriously considered to be artificial signals when they were first detected in 1967. They turned out to be something stranger than intelligence, the natural consequence of stellar death. For the most massive stars, not even a neutron star forms. The core continues collapsing past nuclear density, past any known state of matter, until it reaches a singularity, a point where our current equations break down and the curvature of spacetime becomes infinite. A black hole forms around it, a region of spacetime from which nothing, not even light, can escape once it has crossed the event horizon. A black hole is, in one reading, the ultimate death, the most complete erasure. Matter falls in and nothing comes out, but this is exactly where the story becomes genuinely revolutionary, because this is where Stephen Hawking and his colleagues found something that changed everything. In 1974, Hawking calculated, using a combination of general relativity and quantum mechanics, the two great theories of 20th century physics that have famously resisted unification, that black holes are not entirely black. Quantum effects near the event horizon cause pairs of virtual particles to appear spontaneously as they do throughout space. Under normal circumstances, these particles annihilate each other almost immediately, but near a black hole's event horizon, one particle of the pair can fall in while the other escapes. The escaping particle carries away energy. To an outside observer, the black hole appears to radiate, slowly, steadily, at a temperature related to its mass. This Hawking radiation is real, but for stellar mass black holes, the temperature is so low, far colder than the cosmic microwave background radiation that fills all of space, that the radiation is purely theoretical for now, undetectable by any instrument we have or are likely to build in the foreseeable future. But for the universe's long-term fate, it matters enormously, because Hawking radiation means black holes evaporate very slowly, incomprehensibly slowly, for any black hole of stellar mass. A black hole the mass of our Sun would take roughly 2 times 10 to the power of 67 years to completely evaporate via Hawking radiation. The current age of the universe is approximately 14 billion years, or roughly 10 to the power of 10 years. So, a solar mass black hole would outlive the current age of the universe by 57 orders of magnitude, and supermassive black holes, millions or billions of times more massive, would take proportionally longer. But they do evaporate. Given enough time, and the universe has a great deal of time available, every black hole that currently exists will eventually radiate away all of its mass and vanish in a final burst of high-energy radiation. And this is where the information paradox enters the picture with full force, because what happens to the information that fell into the black hole when it evaporates? Hawking radiation, as originally calculated, is perfectly thermal. It carries no information about what fell in. A black hole that swallowed a library of books would, in this original formulation, emit exactly the same Hawking radiation as a black hole that swallowed an equivalent mass of hydrogen gas. The information would be destroyed, but quantum mechanics says information cannot be destroyed. These two positions are irreconcilable. This is the black hole information paradox, and it is not a minor technical dispute. It is a fundamental conflict between two of the most successful theories in the history of science. Resolving it has occupied some of the most brilliant minds in physics for 50 years. The current best candidate for resolution comes from a somewhat unexpected direction: the holographic principle and its concrete realization in something called the ADS/CFT correspondence, anti-de Sitter space and conformal field theory, a mathematical framework developed primarily by Juan Maldatina in 1997. This work, perhaps the most cited paper in the history of physics, suggests that the information content of a volume of space can be completely described by a theory living on its boundary surface, in the same way that a two-dimensional hologram encodes a three-dimensional image. Applied to black holes, this suggests that the information that falls in is not lost, but is somehow encoded in the Hawking radiation, emitted as the black hole evaporates. Scrambled, yes, impossibly scrambled, from any practical standpoint, but present in principle. The universe keeps its records, even here, even at the most extreme boundary of space-time. This matters philosophically, because it means the universe is not, at any scale, in the business of erasure. The second law of thermodynamics ensures that usable structure disperses, but the information that defined that structure is preserved in some form in the universe's ongoing state. Nothing that was is ever truly gone in the physicist's sense of the word gone. Whether that provides any comfort to conscious beings facing their own dissolution is a separate question, one that requires us to think carefully about what consciousness actually is and what exactly is lost when it ends. Consciousness remains one of the most fiercely contested topics in all of science. We do not have a settled theory of it. We know a great deal about the neural correlates of conscious experience, the patterns of brain activity associated with awareness, attention, and feeling. We know that damage to specific brain regions disrupts specific aspects of conscious experience in highly predictable ways. We know that anesthesia can switch consciousness off and back on with remarkable reliability, even if we do not fully understand the mechanism. We know that the brain consumes roughly 20% of the body's energy while comprising only 2% of its mass, a fact that suggests the maintenance of consciousness is metabolically expensive and therefore presumably important for survival. But we do not know what consciousness is, in the sense that we know what a protein is, or what a photon is. We do not have an equation for it. We do not have a physical theory that explains why there is something it is like to be a conscious organism, why the processing of information in a sufficiently complex nervous system gives rise to subjective experience, to the feeling of being inside a life rather than simply running through one. This is what the philosopher David Chalmers called the hard problem of consciousness, and it remains hard because it seems to require something beyond functional description. You can describe in complete detail how the visual system processes information about color, how it compares wavelengths, how it signals to other brain regions, and you still seem to have said nothing about why any of that gives rise to the experience of seeing red. The experience itself, the qualia, as philosophers call them, seems to sit outside the functional description. There are broadly two camps on this question among scientists and philosophers. The first holds that consciousness is entirely a product of physical processes, that when we have a complete enough description of brain activity, the subjective experience will be fully explained, and the apparent gap between description and experience is an illusion created by our limited perspective. This is the materialist or physicalist view, and it is held by the majority of neuroscientists. The second camp holds that consciousness cannot be fully reduced to physical processes, that there is something genuinely extra in experience, something that physical description leaves out. Within this camp, there are many positions, from property dualism, which holds that consciousness is a non-physical property that nevertheless emerges from physical systems, to panpsychism, which holds that some form of experience is a fundamental feature of all matter, not something that emerges from complex organization, to outright dualism, which holds that mind and matter are genuinely separate substances. Physics, interestingly, has been flirting with some version of the second camp in recent decades, though the flirtation is cautious and contested. The physicist Roger Penrose, in collaboration with the anesthesiologist Stuart Hameroff, proposed in the 1990s that consciousness arises from quantum processes in structures called microtubules within neurons, tiny cylindrical protein structures that form part of the cell's internal scaffolding. Their theory, called orchestrated objective reduction, or OR, proposes that quantum coherence in these microtubules gives rise to moments of conscious experience through a process that involves what Penrose calls objective reduction, a specific kind of quantum state collapse that he believes is not fully described by current quantum mechanics and may require a new theory that unifies quantum mechanics with general relativity. OR is controversial, very controversial. Most neuroscientists and physicists regard it with deep skepticism, partly because maintaining quantum coherence in the warm, wet, noisy environment of a neuron seems extraordinarily difficult. Quantum effects are notoriously fragile, and partly because the theory makes specific predictions that have not been confirmed. But it has not been definitively ruled out either, and some recent experiments on photosynthesis, bird navigation, and enzyme function have shown that quantum coherence can play functional roles in warm biological systems, which had not been expected. More broadly, the question of whether quantum mechanics is relevant to consciousness is genuinely open. We do not know enough about either consciousness or quantum mechanics, particularly the quantum measurement problem, which concerns how quantum superpositions become definite classical outcomes, to close the door on connections between them. But here is what we do know about what happens to the brain when it dies, and what we know is detailed, clinical, and in certain respects, genuinely strange. The brain is among the most energy-hungry organs in the body. It requires a continuous supply of oxygenated blood to maintain the electrochemical gradients that allow neurons to fire. When blood flow stops, as it does in cardiac arrest, neurons begin to lose these gradients within seconds. Within about 4 to 6 minutes without oxygen, brain cells begin to die in the most metabolically active regions first. The hippocampus, critical for memory formation, is among the most vulnerable. The cortex follows. The brainstem, which controls breathing and heart rate and is generally the last part of the brain to go, is more resistant, though it too fails without blood supply. This process is not uniformly instant, and this is where things become scientifically interesting. The transition from alive to dead is not a moment, but a process, a cascade of failures that can, in the early stages, be reversed. Cardiopulmonary resuscitation can restore circulation and allow the brain to recover if started quickly enough. Advanced cooling techniques can extend the window for recovery by slowing cellular metabolism. Hearts have been restarted after being stopped for extended periods. The question of exactly when death becomes irreversible is not merely philosophical. It has direct clinical consequences and is the subject of active research. In 2023, a study published in the Proceedings of the National Academy of Sciences reported something remarkable. In patients who suffered cardiac arrest and were not resuscitated, researchers monitoring brain activity recorded a surge of high-frequency gamma waves in the minutes after the heart stopped. Gamma waves are associated in healthy conscious brains with states of heightened awareness and complex information integration. The finding was reported in 4 patients, a very small sample, but it replicated and extended a similar observation made in rats in 2013. In the rats, the researchers had seen a broad surge of highly organized neural activity following cardiac arrest, more organized in some measures than the waking brain's activity. The interpretation of these findings is deeply contested. The researchers who conducted the human study explicitly did not claim that the patients were having near-death experiences. They noted that the brain activity was detected in regions associated with conscious processing, the posterior cortical hot zone, an area implicated in the neural correlates of consciousness, but that they could not determine what, if anything, the patients were subjectively experiencing. The findings were, in their framing, consistent with the hypothesis that the dying brain might generate intense conscious experience, but they were not proof of it. This connects to a broader body of literature on near-death experiences, which is far more scientifically rigorous than popular accounts might suggest. The AWARE study, Awareness, during resuscitation, led by the cardiologist Sam Parnia, ran for 4 years across multiple hospitals in the UK, US, and Austria, and sought to verify or falsify reports of out-of-body experiences during cardiac arrest by placing hidden targets on high shelves in cardiac arrest bays, images that could only be seen from a viewpoint above the patient's head. Of the patients who survived cardiac arrest in the study, a significant number reported some form of awareness during their resuscitation, including sensations of peace, by seeing light and reviewing their lives. A smaller number reported specific perceptions during the period when they were clinically dead, when their hearts had stopped and their brains should have been silent. Only 1 patient reported an out-of-body experience, and of those cases, the hidden target was not verified. The study could not confirm veridical perception during cardiac arrest, but it documented in rigorous detail that a substantial fraction of cardiac arrest survivors report some form of conscious experience during clinical death, and that these experiences are often described as more vivid and real than ordinary experience, not less. The standard scientific explanation for near-death experiences does not require anything beyond known neurophysiology. The brain, starved of oxygen, may generate hallucinations. The specific content of these hallucinations, the tunnel, the light, the life review, the feeling of peace, may reflect the architecture of the dying brain's activity. The orderly activation of visual cortex as inhibitory interneurons die first, creating the impression of a brightening light, the flooding of the limbic system with disinhibited activity, producing the feeling of profound emotional significance, the activation of memory networks, producing the review of autobiographical events. These are plausible mechanisms. They are not proven, but they fit within the existing framework of what we know about the brain. The remarkable feature of near-death experiences is not that they prove something beyond ordinary neuroscience, but that they reveal how the dying brain is not simply fading to static. It may be generating some of the most intense and organized experiences of its entire existence in its final moments. What happens after those moments? After the cardiac arrest is not reversed, after the neurons have exhausted their remaining energy reserves, after the membrane potentials collapse and cannot be restored, is the end of what we recognize as a person. The particular pattern of neural connectivity accumulated over a lifetime of experience, the specific weighting of synaptic strengths that encoded memory and personality and habit, begins to degrade. The information is not destroyed in the quantum sense, but it is no longer instantiated in any functioning pattern. The brain dies, but the atoms of which that brain was composed continue their existence. Carbon, hydrogen, oxygen, nitrogen, phosphorus, calcium, the major elements of biological tissue, disperse into the environment in ways that depend on what happens to the body. In a natural burial, microorganisms begin to break down biological molecules almost immediately. The carbon enters soil and eventually the atmosphere. The nitrogen is used by bacteria and plants. The minerals leach into groundwater or are incorporated into soil. Over timescales of decades to centuries, essentially all of the body's mass has been redistributed into the environment, into water, soil, air, and other living organisms. The atoms themselves are ancient. The carbon in your body was forged in the cores of stars that died before our solar system formed, in the triple alpha process, where 3 helium nuclei fuse to form 1 carbon nucleus, an extraordinarily improbable reaction that nevertheless proceeded at scale in the cores of dying red giants. The oxygen that composes the water in your body was also produced in stellar fusion and scattered into space by supernovae. The iron in your blood was made in the core collapse of a massive star. The heaviest elements require the violence of a supernova or a neutron star merger to form. You are, in the most literal sense, made of dead stars. This is not poetry, it is nuclear astrophysics. Every atom in your body, heavier than lithium, was forged in a star, and every star that contributed to your making is now dead. Its matter scattered, redistributed, cycled through nebulae and solar system formation and planetary geology and ocean chemistry and biological evolution until it arrived, temporarily, in you. This recycling is not incidental to the universe's operation, it is fundamental to it. Stars are how the universe creates the elements necessary for chemistry complex enough to generate life. Without stellar death, without supernovae and their dispersal of heavy elements, there would be no carbon-based chemistry, no water, no rocky planets, no organic molecules. Life is downstream of stellar death. In a very real sense, you owe your existence to the deaths that preceded you, going back to the first generation of stars, 13 billion years ago. And when you die, you contribute to this process. Your atoms join the reservoir from which future chemistry will be assembled. Not in any planned or purposeful way. The universe has no agenda, but the material does cycle. The hydrogen atoms in your body will persist in various forms until the far future of the universe. The protons of which they are composed may persist even longer, depending on whether protons decay, a question that current physics cannot definitively answer, though experiments have constrained the proton lifetime to be longer than approximately 10 to the 34th years. This brings us to the very long view, to what cosmologists call the deep future, the unimaginably vast stretches of time after everything familiar has ended. The current era of the universe is called the stelliferous era, the age of stars. It began roughly 1 million years after the Big Bang, when the universe had cooled enough for gravity to pull gas into dense clouds that ignited into fusion. It will end in perhaps 100 trillion years, when the last low-mass red dwarf stars, the most frugal consumers of hydrogen, burning so slowly and coolly that they can shine for vastly longer than more massive stars, finally exhaust their fuel and fade. During this immense span of time, the universe will continue doing what it has been doing, forming stars from clouds of gas, allowing those stars to synthesize heavy elements and scatter them in death, allowing new generations of stars to form in enriched nebulae. But the raw material is finite and the process lossy. Stars convert hydrogen and helium into heavier elements that are less useful for further fusion. The total amount of gas available for star formation decreases over time as it is locked up in stellar remnants. The stelliferous era is not uniform, it is a gradual dimming, star formation rates declining over hundreds of billions of years, the last stars forming perhaps 1 trillion years from now. After the last star fades, the universe enters what cosmologists call the Degenerate Era. The stellar remnants, white dwarfs, neutron stars, black holes, and dark objects continue orbiting in the remnants of galaxies, or rather, in the loose clouds of cold matter that were once galaxies. Even without new stars, the universe is not entirely dead in this era. To brown dwarfs, objects that never quite had enough mass to ignite fusion, might still experience occasional nuclear reactions from cosmic ray impacts or from the rare quantum tunneling events that could trigger fusion even at very low temperatures. White dwarfs cool slowly, radiating away their residual heat over trillions of years. The universe is fading, but not instantly. Gravitational interactions within these clouds of remnants will, over extremely long timescales, cause objects to either be ejected from their host systems or to spiral inward and collide. Most stars, even in dense clusters, are eventually ejected by the gravitational slingshot effect. Interactions that give one object a boost at the expense of another's orbital energy over timescales on the order of 10 to the 23rd years, vastly longer than the current age of the universe. Gravitational interactions will have scattered most of the mass in galaxies into intergalactic space, leaving only the central black holes. These central black holes, now surrounded by nearly empty space, will slowly evaporate via Hawking radiation over timescales that depend on their mass. For a black hole of 1 billion solar masses, roughly the mass of a modest supermassive black hole, the evaporation timescale is on the order of 10 to the 93rd years. For the most massive supermassive black holes observed, billions of solar masses, the evaporation would take correspondingly longer, but it will happen. Given enough time, every black hole evaporates into a diffuse bath of photons and other elementary particles. This is the black hole era, and when it ends, the universe enters what physicists call the dark era, a time so remote from the present that even the concept of calculation becomes strange. The universe is filled with an extraordinarily dilute gas of photons, neutrinos, electrons, and positrons, the final remnants of all the black holes and all the matter that has evaporated or decayed. The photons are redshifted to such low energies that the universe is effectively cold, dark, and empty. Entropy is near its maximum value. The organized structures that once filled the cosmos, galaxies, stars, planets, cells, thoughts, are irretrievably smeared across the entire volume of the observable universe. Is this the end? Probably, but not certainly. Here is where physics leaves the security of well-tested theory and enters the domain of speculation, where the arguments are rigorous, but the empirical support is thin. There are theoretical reasons to think that the dark era is not perfectly static. Quantum mechanics permits spontaneous fluctuations in quantum fields, virtual processes that create temporary configurations of matter and energy from the vacuum. In an infinitely large and infinitely old universe, the Boltzmann brane problem arises. Quantum fluctuations will, given enough time, spontaneously assemble configurations of matter that are arbitrarily complex. The philosopher Ludwig Boltzmann noted in the 19th century that thermal fluctuations in a gas at equilibrium will, given sufficient time, spontaneously produce any configuration, and including configurations of extremely low entropy. Applied to the far future universe, this means that, eventually, after timescales so vast they make the black hole evaporation times look like a brief afternoon, quantum fluctuations will spontaneously produce structures, perhaps small ones, like hydrogen atoms, perhaps over times that beggar the imagination, larger ones, perhaps, given genuinely infinite time, even self-aware structures, what cosmologists and philosophers call Boltzmann brains, momentarily assembled minds that spring into existence from random quantum fluctuations, experience a brief moment of consciousness, and then dissolve back into the void. The Boltzmann brane problem is taken seriously, not as a prediction of what the universe will produce, but as a constraint on cosmological theories. If a theory predicts that Boltzmann branes are more numerous than actual evolved observers, as some versions of eternal inflation cosmology seem to, then the theory is in trouble because we are not Boltzmann branes, and we have good reason to believe this. The problem is real and has produced a significant body of technical literature, but set the Boltzmann brane puzzle aside and consider a different and perhaps more immediately interesting question. What does the inflationary cosmology that currently represents the scientific consensus say about the large-scale structure of reality, and how does that bear on questions of death and ending? Inflationary cosmology holds that, in the earliest instance after the Big Bang, fractions of a second so small they are difficult to write in ordinary notation, the universe underwent a period of exponential expansion. doubling in size repeatedly over a time that makes our current 13 billion year history look like an afterthought. This inflation was driven by a quantum field, the inflaton field, which was in a high energy state that drove space-time to expand at a furious rate. Inflation ended in our observable universe about 10 to the minus 32 seconds after the Big Bang, when the inflaton field rolled down to its minimum energy state and converted its energy into the matter and radiation of the hot Big Bang. But many physicists believe inflation did not end everywhere simultaneously. In the eternal inflation model, quantum fluctuations in the inflaton field cause some regions to inflate more than others, creating an endless self-reproducing cosmos in which our observable universe is a single bubble within an infinite sea of inflating space-time. In this picture, there are infinitely many bubble universes, each with their own local physics, their own versions of the constants of nature, their own laws. Most of these bubbles would be hostile to any form of complexity, but some, by random variation, would have physics hospitable to chemistry and stars and life. The observable universe we inhabit is, in this framework, one such hospitable bubble, and we observe it because we are the kind of thing that can only form in a hospitable bubble. The multiverse picture is controversial. It makes predictions that are, at present, extraordinarily difficult to test. Some physicists regard it as science. Others regard it as metaphysics wearing science's clothing. But it is taken seriously by a significant fraction of the theoretical physics community, including many of the founders of inflationary cosmology. If the multiverse is real, then death, even the death of the entire observable universe, is not the death of everything. The larger structure of the inflationary cosmos continues, spawning new bubbles, new regions of low entropy, new opportunities for the emergence of complexity. The universe as a whole does not die because the universe as a whole is not a bounded thing. It is an ongoing, self-reproducing process. This is, in a sense, a scientific argument for a form of cosmic immortality, not for any individual, not for any civilization, but for the project of complexity and organization, and perhaps consciousness itself. Somewhere, in some bubble universe, something is always just beginning. But this kind of comfort, if comfort is even the right word, is very cold. It operates at scales so far from human experience that it offers no consolation for the specific, personal, devastating fact of individual death. The fact that somewhere in a bubble universe, a consciousness is experiencing its first moment of awareness does nothing to soften the loss of this specific consciousness, this specific history, this particular person. To think about individual death scientifically, we have to return to the brain and to a set of questions that neuroscience is only beginning to be able to address. What is the relationship between the physical structure of the brain and the specific experiences of a specific life? Memory, we now know, is not stored in single neurons. It is stored in patterns of connectivity, in the strength of synaptic connections between neurons, in the precise topology of who connects to whom and how strongly. A single memory, the sound of a particular voice, the taste of a particular food, the feeling of a particular afternoon, is encoded in a distributed pattern of synaptic weights across potentially millions of neurons. Damage one neuron and the memory may be only slightly degraded. Damage the entire network and it is gone. This distributed encoding is both a source of resilience and a source of something philosophically significant. The self, the sense of continuous identity over time, is similarly distributed. It is not located in any single structure, though some structures are more important than others. The hippocampus plays a critical role in forming new memories and in binding episodic memories to their context. The prefrontal cortex is crucial for the integration of memory, planning, and self-referential thought. The default mode network, a set of regions most active when the brain is not focused on external tasks, is associated with self-referential thinking, autobiographical memory, and the sense of being a continuous self over time. Damage to these systems produces characteristic disruptions to the sense of self. Severe damage to the hippocampus, as in the famous case of patient HM, who had his hippocampi removed to treat epilepsy in 1953, leaves the person unable to form new long-term memories while preserving memories from before the damage. HM could carry on a conversation, could learn new motor skills, but could not remember meeting someone the previous day. His sense of self was frozen at the point of the surgery. He remained, in some important sense, the person he was before. Same personality, same humor, same preferences, but he could not accumulate new experience into his autobiographical narrative. What this tells us is that the self is, at least in significant part, a story, a narrative assembled from episodic memories, woven together by the structures of the brain into something that feels continuous and unified, even though it is distributed and reconstructed anew each time it is accessed. The neuroscientist Antonio Damasio has argued that the self is not a thing so much as a process, an ongoing, dynamic construction that the brain performs continuously. The core self, in his model, is generated anew at each moment by the brainstem's mapping of the body's internal state. The autobiographical self is a higher-level elaboration that adds the narrative dimension, the sense of being a particular person with a particular history, moving through time. If the self is a process, then its end is the cessation of that process. The atoms that composed it persist. The information that was encoded in its synaptic structure is scrambled and redistributed into the environment. The process itself, the ongoing construction of experience and narrative, stops. What is lost? Everything that was unique to that process. The specific configuration of memories, the particular weighting of associations, the distinct texture of a specific inner life. This is not recoverable from the atoms, any more than the text of a burned book is recoverable from its ashes, not because the information is destroyed in the quantum sense, but because the particular organization that gave it meaning is gone, and the information is dispersed across systems that will never spontaneously reassemble it, unless, and here science enters territory that it has barely begun to explore, unless that information can be preserved or reconstructed. The field of mind uploading, or whole brain emulation, is currently more philosophy than engineering, but it is not entirely without scientific basis. The connectomy, the complete map of neural connections in a brain, is in principle a physical object that could be measured. Technologies for mapping neural connectivity are advancing rapidly. Electron microscopy can resolve individual synapses. Expansion microscopy allows brain tissue to be physically enlarged for higher resolution imaging. New computational tools for reconstructing three-dimensional neural architectures from two-dimensional slice data are becoming increasingly powerful. The Human Connectome project produced detailed maps of large-scale connectivity in the living human brain using advanced MRI techniques. More recently, researchers have produced nanoscale connectomy maps of small volumes of cortex. A cubic millimeter of mouse cortex, mapped at synaptic resolution, contains roughly 100,000 neurons and 1 billion synaptic connections, and took years of computation to reconstruct even at that small scale. Mapping the full human connectome at synaptic resolution, all 86 billion neurons and their estimated 100 trillion synaptic connections, is beyond current technology by many orders of magnitude. But the gap is narrowing, and the question it raises is genuine. If you could perfectly capture the connectivity pattern, the synaptic weights, the molecular state of every neuron in a brain, the full information content of that specific mind, would you have captured the person? Would running that information on a different substrate constitute continuation of existence, or the creation of a very detailed copy? This question is the technological face of a deeper philosophical puzzle, the question of personal identity over time. You are not the same collection of atoms you were 7 years ago. Most of your cells have been replaced, and even in cells that persist, the molecules composing them are constantly turned over. What makes you the same person as the child in your earliest memories? It cannot be material continuity. It must be something about the continuity of pattern, of information, of the ongoing process. If that process can be transferred to a different substrate without interruption, many philosophers argue, the person continues to exist. If the process is stopped and restarted, even on the same substrate, the continuity may be broken. These are not idle philosophical puzzles. They have direct bearing on how we think about death, because if personal identity is fundamentally about informational continuity rather than material continuity, then death is not necessarily the end of the person. It is the interruption of the information processing pattern. Whether that pattern could in principle be restored depends on whether the information was preserved with sufficient fidelity. Cryonics organizations have argued for decades that death need not be permanent, that if a person's brain can be preserved immediately after clinical death, before the neural architecture has degraded, the information content of that brain might be recoverable by future technology sufficiently advanced to interpret and restore it. The science of cryopreservation has advanced considerably since the early days. Vitrification, which replaces cellular water with a glass-forming solution before cooling, prevents the ice crystal formation that destroys cellular structures during conventional freezing. Researchers have vitrified and revived organs successfully. The small roundworm C. elegans has been vitrified, revived, and shown to retain learned behaviors, suggesting that at least some informational structure can survive the process. Whether any of this will eventually translate to the preservation of human brain connectivity at the level of detail required for mind reconstruction is genuinely unknown. The hurdles are enormous, but the arguments are not obviously wrong, and some serious scientists take them seriously. The physicist Freeman Dyson thought carefully about the long-term fate of consciousness in the universe and proposed in a 1979 paper in Reviews of Modern Physics that life might survive the heat death of the universe by gradually slowing its metabolism as the universe cools, thinking fewer and fewer thoughts per unit of time, but potentially thinking forever, as long as there remained some gradient of energy to exploit. Dyson was careful about the speculative nature of the argument, but it illustrated a point that subsequent cosmologists have found important. The long-term survival of information processing systems is not obviously forbidden by physics. Subsequent work has complicated Dyson's picture. The accelerating expansion of the universe, driven by dark energy, poses problems for his scenario by eventually cutting off the energy gradients he imagined being exploited. But the broader question he raised, what are the ultimate limits on the existence of complex information processing systems in a universe subject to the second law, remains open and actively discussed. The physicist Lawrence Krauss and cosmologist Glenn Starkman argued in 2000 that life in an accelerating universe is fundamentally finite, that the available energy and information processing capacity within any observer's causal horizon eventually decreases to zero, making indefinite existence impossible. But other physicists have found loopholes or questioned the assumptions. The debate is not settled. What is settled, or at least what the current consensus of cosmological evidence strongly suggests, is that the observable universe is accelerating in its expansion, driven by dark energy, and that this accelerating expansion will eventually carry all galaxies beyond our cosmic horizon. The universe will not end in a big crunch, collapsing back on itself, as was once considered possible. Instead, it will continue expanding forever, as its galaxies separating beyond causal contact, its stars burning out, its black holes evaporating. The Milky Way and Andromeda will merge in about 4 billion years, before the Sun exhausts its hydrogen in about 5 billion years, expanding into a red giant that will engulf Mercury, Venus, and possibly Earth. After the Sun becomes a white dwarf, the solar system's remaining planets will be left orbiting a slowly cooling ember. On the scale of the universe's future history, the entirety of human civilization, all 5,000 years of recorded history, all the art and science and philosophy and war, all the love and grief and beauty that humans have managed, occupies a moment so brief it cannot be depicted on any timeline drawn at a scale legible to human eyes. The age of stars will continue for 100 times the current age of the universe. The age of stellar remnants will last 100,000 times longer than that. The age of black hole evaporation will last longer still, by factors that require scientific notation to express. And yet, here we are, in this particular moment, able to calculate all of this, able to sit at the beginning of the stelliferous era and work out the endpoint of reality with algebra and physics. The consciousness that emerged from stellar debris can model the processes that produced it, trace those processes forward to their conclusion, and reflect on what it means. This capacity to model the universe, including one's own origins and ending, is not obviously demanded by natural selection. Evolution needed humans to survive long enough to reproduce, and not to calculate the evaporation time of black holes. Our capacity for abstract reasoning, for science, for this kind of deep self-reflection appears to be a byproduct of cognitive machinery built for other purposes. And yet, it has given us something extraordinary, the ability to stand outside the universe's processes, in some sense, and see them whole. The philosopher Thomas Nagel argued in his famous essay, "What is it like to be a bat?" that there is something irreducibly subjective about experience, something that objective, third-person description can never fully capture. Whatever happens in the universe at the level of atoms and fields and space-time, there is also the fact of experience, the first-person reality of being something, of being here, of this specific moment, in this specific mind. The universe described by physics is a universe of patterns and processes and information, but from the inside, there is also the universe of experience, the sound of wind, the weight of grief, the particular quality of understanding something for the first time. Science can tell us what happens to the atoms. It can tell us what happens to the information. In the physical sense of that word, it cannot yet tell us what happens to experience, not because it is obviously something beyond physics, but because we do not yet have a physics of experience. The hard problem of consciousness is hard precisely because we do not know how to connect the objective description of neural processes to the subjective reality of what those processes feel like from the inside. This gap between the physical story and the experiential story is where most of the deepest questions about death live, not in the question of what happens to atoms, which we understand well, or even in the question of what happens to information, which we understand at least in broad outline, but in the question of what happens to this, to the specific, unrepeatable quality of being here, of being conscious, of being this particular arrangement of matter and energy that is aware of itself and of the world around it. Some scientists and philosophers think this gap will close, that a complete physics of consciousness will eventually explain not just what the brain does, but why it feels like something to have a brain doing those things. Others think the gap is ineliminable, that experience is genuinely irreducible, that the universe has both a physical face and an experiential face, and that a complete theory of reality will have to account for both. What we can say with confidence, standing on the current knowledge of physics and neuroscience and cosmology, is this: nothing that has ever existed has been destroyed. Everything has been transformed. The atoms of the first stars are still here, cycling through the universe's ongoing processes. The information that defines any physical system, including a conscious mind, is preserved in principle by the laws of quantum mechanics, even as it disperses into forms that become practically irrecoverable. The universe's history is written in its present state. We can also say that death at every scale, the death of a neuron, the death of a person, the death of a star, the eventual death of the stelliferous era, is a transition in the organization of matter and energy, not its destruction. The transition is real and often irreversible in any practical sense, but irreversibility and destruction are not the same thing. The pattern of a person's life, encoded in the neural connections of a brain, does not survive the death of that brain in any form that any current or foreseeable technology could reconstruct. But in the mathematical physics of a fully quantum mechanical universe, that information was not destroyed. It was smeared across the environment in a form that no actual intelligence will ever decode. Whether that constitutes any form of survival depends entirely on what you think matters. If what matters is the specific subjective experience of this particular mind, then its end is its end, and nothing in physics suggests otherwise. If what matters is the persistence of information in some form, then physics offers a kind of strange cold comfort. If what matters is the recycling of matter, then the atoms go on forever, in various forms, for timescales that make the current age of the universe look like a brief prelude. And if what matters is the continuation of the project of consciousness itself, the universe's apparently improbable capacity to generate arrangements of matter capable of modeling themselves and the cosmos they inhabit, then that project, while finite in any given location, may be effectively open-ended in the full inflationary cosmology. Other bubbles form. Other stelliferous eras begin. In those bubbles, physics may be different, chemistry may be different, life may be different, but the possibility of complexity, of organized information, of experience, that possibility is built into the laws of physics as we know them, and there is no reason to think those laws are unique to our bubble. None of this makes individual death less difficult. The specific loss of a specific person, the silencing of a specific voice, the ending of a specific history is not made less by knowing that the atoms continue, or that quantum information is conserved, or that other universes bubble into existence. Loss is real. The ending of a conscious life is a real ending, even if it is not an absolute one in the cosmic ledger. But there is something in this picture that is, if not comforting, then at least clarifying. We are, each of us, a temporary arrangement of ancient matter. Matter that has been through the cores of stars, through the violence of supernovae, through billions of years of cosmic cycling. We are the universe's way of being locally organized for a time. The organization ends, the matter continues, the information disperses, but for a while, for the span of a human life, that specific arrangement of matter was here, was aware, was looking out at the same universe from which it was made, and was able to understand something about itself and its origins. This is not nothing. In a universe that will spend the overwhelming majority of its history in cold darkness, the stelliferous era, the brief age of stars, is when everything interesting happens, when chemistry becomes possible, when planets form, when the first proteins fold, when the first nervous system generates the first flicker of experience. We are in the middle of this extraordinary and improbable window, and in this window, for a lifetime, each conscious being holds within it a particular view of the cosmos, a view that will not exist again when that window closes. The physicist Richard Feynman, late in his life, was asked what he thought happened after death. He said that he thought nature would not be so unimaginative as to allow him to exist only once, but he said it lightly, acknowledging it was not something he could calculate. What he did say with conviction was that the experience of being alive and curious and able to understand things was itself extraordinary, something to be savored for exactly what it was, without the need to extend it beyond its natural span. There is a view of the universe supported by physics, by cosmology, by what we know of the brain and the processes of life and death, that sees all of this not as a story of loss, but as a story of transformation at staggering scale. The universe is not a static container in which things happen and are then permanently gone. It is a dynamic process in which everything that has ever happened continues to shape everything that is happening now and everything that will happen in the future. The light from a supernova that exploded 1 billion years ago is still traveling through space. The elements that supernova scattered have been incorporated into planets and atmospheres and organisms and thoughts. The history of the universe is not in the past. It is in the present, written in the arrangement of everything that exists. Death, in this view, is not a departure from the universe, but a deep participation in it. The organized system that was alive returns to the wider processes from which it temporarily separated itself. Its matter joins the broader cycling of matter. Its information, scrambled and distributed, is woven into the present state of the universe in ways that cannot be read but cannot be erased. Whether this is enough, whether this vision of cosmic recycling and information conservation is a satisfying account of what happens to us, to each of us, when we die, is not a question that science can answer. Science can tell us what happens to the atoms. It can tell us what happens to the information. It cannot tell us what happens to the experience, or whether that question even has a physical answer. That gap between the third-person story of physics and the first-person reality of experience is the deepest open question at the intersection of science and human existence. What we can say is that the universe as physics reveals it, is stranger and richer than any simple story of endings allows. From the perspective of a neutrino passing through the Earth at nearly the speed of light, from the perspective of a quantum of light that has traveled 13 billion years from the surface of the last scattering, from the perspective of an electron in a superconductor experiencing quantum coherence, the universe is full of processes that our ordinary intuitions about time and causation and identity were not built to handle. We are large, slow, warm, classical objects, evolved to navigate a particular range of scales, a particular range of energies. Our intuitions about death are shaped by this limited perspective. We see endings because we see at the scale at which endings are real. At the atomic scale, there are no endings, only rearrangements. At the quantum scale, information is conserved. At the cosmic scale, matter cycles through forms on timescales that make death look like a momentary fluctuation. None of this denies the reality of what happens to a person when they die, on the scale at which persons exist, but it places that reality in a context that is genuinely larger, not as a consolation, but as a more complete and accurate picture of what kind of thing we are and what kind of universe we live in. We are the universe becoming briefly aware of itself, looking back at its own history, calculating its own future, asking questions that the universe's own processes have only recently generated the capacity to ask. We are made of atoms forged in stellar deaths. We are powered by a star. We live on a rock assembled from the debris of a molecular cloud. We breathe an atmosphere that was partially built by bacteria over billions of years. We think with an organ shaped by hundreds of millions of years of evolutionary pressure, in a brain whose architecture still carries the marks of ancestral nervous systems from long before there were creatures that could wonder about the cosmos. And when we die, we return to those processes, to the cycling of matter and the conservation of information and the ongoing transformation of the universe's structure. We go back to the stars in the most material sense. The carbon returns to the carbon cycle, and eventually, when the sun becomes a red giant and the inner solar system is vaporized, the carbon of our bodies will be returned to space to join the interstellar medium, to perhaps contribute to a future generation of stars. In 100 trillion years, the last red dwarf will fade. In 100 times 10 to the 67th years, the last stellar black holes will have evaporated. In times that cannot be meaningfully named in any human language, the universe will be cold and dark and close to its maximum entropy. But the history of everything that happened during the stelliferous era, the history of stars and planets and life and thought and love and grief, will be encoded, impossibly scrambled, but never destroyed, in the quantum state of whatever remains. The universe remembers, not in any way that can be read, not in any way that comforts a particular mind in a particular life, but in the physicist's sense, in the deepest sense that the laws of nature allow, nothing is ever truly gone. What happens after death, according to science, is everything. The atoms continue, the information disperses. The universe goes on, carrying the imprint of everything that was, and somewhere, in some corner of the cosmos, something else is just beginning to look up